Hello and welcome again to my Physical Science Online Lecture Supplement series. In today's video, I wanted to work through a few examples which I have come up with as supplements to the physical science text by Shipman, Wilson, Higgins, and Torres, which we are using in the online course. Before beginning those examples, it's worth making a little equation sheet for ourselves. The publisher, for example, gives you a set of equations at the back of each chapter of text that are the important equations for the text. So here are those in case you want them for reference. So on to the examples. The first example that we have for this course is that you have a man who pushes a block along a flat, level, frictionless surface with a horizontal force of 120 newtons for a distance of 5 meters. And what we want to know is how much work is done on the block. So to start off, it's worth maybe drawing a little diagram of what's going on in this problem. So here's our man. He's pushing upon the block. He's pushing the block along a frictionless level ground. Looks like I drew it sloping up a little bit. That's just my bad drawing. But this is supposed to be frictionless and level. And he is pushing with a force of 120 newtons in the horizontal direction. And he pushes the block for a total of 5 meters. So let's put on our 5.0 meter push distance. We want to know how much work he does. So we use that work is equal to the parallel force times the distance over which the object has been pushed. So this would be like how much horizontal distance. This one right here is how much, this is how much horizontal force. This is how much horizontal distance he's traveling across in this case. So that is 120 newtons. And then times 5.0 meters. So you can plug those guys into your calculator if you can't just do it mentally. So 120 times 5 should be 600. So he's done 600 joules worth of work on this object. Okay, so second example, what happens if the man pushes with a total force of 75 newtons and across a total distance of 8 meters, again along flat level frictionless ground. But this time he's pushing at an angle 60 degrees above the horizontal. So now we need to know how much work is being done on the block. So let's draw this thing out. We'll start off by drawing the man pushing upon the block. And this time we'll try to label our forces as having a particular direction. So the block is right here. And this time he's pushing on the block at some angle. So here's our 75 Newton force, but this is at 60 degrees. Note that I'm not necessarily drawing stuff to scale here. Pushing across level ground for a distance of 8 meters. So 8.0 meters. Okay, so we use the same work equals parallel force times distance thing that we used in the previous example, but now we have to get the parallel force from the fact that there's an angle involved as well as a magnitude. So the parallel force is going to be found by using a little bit of trigonometry. So let's draw off to the side here a little triangle for ourselves. Triangle basically is like this. So these two are perpendicular. Here's your 60-degree angle. This one is 75 newtons. And the parallel part is this lower part. So this is adjacent to the angle. This one would be opposite. This one here is actually the hypotenuse. Okay, sorry for the bad handwriting. You want to know what's the adjacent, so we need to use trigonometry like I said. So there's cosine, sine, and tangent. Since it's adjacent and hypotenuse, we need to use cosine. So cosine of an angle is always going to be the adjacent side length divided by the hypotenuse. And the cosine in this case is 60 degrees. The angle in this case is 60 degrees. So the work becomes 75 newtons times cosine of 60 degrees. This part right here basically comes from the fact that we're looking for the adjacent, and to get the adjacent you can multiply the hypotenuse times the cosine. Okay, and then we push it across 8 meters. So plug these guys into your calculator if you need to in order to get our number out. So let's see, 75 times, we want to have the cosine of 60, which should be a half. On my calculator you enter the angle and then you push cosine. Then you multiply that by the 8 meters that you push it across, and we get 300 joules. So the total work done in this case is 300 joules. Okay, so those are a couple examples that have to do with work. Now let's look at a few that have to do with kinetic energy. The first one will be this example 4.3. You have a man whose mass is known and whose speed is known. We want to know what is his kinetic energy. Okay, in this case, a diagram isn't really going to be that useful to us because we can just use the kinetic energy equation. The kinetic energy equation basically says that the kinetic energy is 1/2 times the mass of the object times the speed squared. Since this guy is 72 kilograms, of mass, and he has a speed of 5.0 meters per second. We need to square that number. So let's see, we plug these guys into the calculator. What we get is 72 divided by 2 times 5 squared is 900. So the kinetic energy of this man is 900 joules. Next up, we've got a car who has a mass of 650 kilograms. It's slowing down from a speed of 20 meters per second to a speed of 10 meters per second, and so we want to know how much kinetic energy has been lost. And then secondly, we want to know how much force is required to do this over a distance of 97.5 meters. Okay, so the car had a mass of 650 kilograms. So let's put m car equals 650 kilograms. It had an initial speed of 20 meters per second. It had a final speed of 10 meters per second. And we want to know what is the change in kinetic energy. So change in kinetic energy is going to be whatever is the final kinetic energy minus whatever is the initial kinetic energy. Okay, so the final kinetic energy is going to be given by 1/2 mv final squared. So that's 1/2 times 650 kilograms. That's the mass, times the final speed, which was 10. So times 10 meters per second, and that has to be squared. So let's go ahead and get what that value is. So 650 divided by 2 times 10 squared, which is basically times 100. Oops, I hit a divided by there. Okay, so the total energy is going to be 32,500. So that's how many joules we have as the final energy. Okay, so E final is 32,500 joules. Now we got to repeat for the initial energy. So to do that, these are both for kinetics. We use 1/2 mv initial squared. So that's 1/2 times 650 kilograms times 20 meters per second. That thing's squared. So our initial kinetic energy is going to be 650 divided by 2 times 20 times 20, 130,000. So now we have our initial and our final energies. And now we can plug those two up here into this blank space that we used. So that is going to be 32,500 joules minus 130,000 joules. So our change in kinetic energy we can get by subtracting these two from each other. Should be 97,500. So we write down here 97,500 joules. Okay, so that is our answer to the first part of this problem. Remember though that there's actually a second part of the problem. Specifically, we wanted to know how much force is required to slow this car down over a distance of 97.5 meters. So we're assuming, of course, that the force is constant. The problem, therefore, becomes figuring out how much force that is that needs to be applied over those 97 meters. We already found that the total change in kinetic energy is 97,500 joules. It turns out that change in kinetic energy is basically done entirely due to work. That's called the work energy theorem. So this is also equal to how much work is done. And then secondly, we have that the work is equal to the force times the distance, which means that the parallel force is also equal to the work divided by the distance. Okay, we'll assume here that whatever force is being applied is in fact parallel to the distance over which the car is moving. That's usually the case. For example, if you're applying the brakes, then the force will be exactly in the opposite direction the car is moving, in which case the parallel force and the total force are equal. In any case, what this means is that we have a force of which is equal to 97,500 joules divided by 97.5 meters. Okay, so by my math, that's going to be 1,000 newtons. If you want to double check that with a calculator, 97,500 divided by 97.5 gives you 1,000. One more problem on these notes, which is what happens if the car of mass 650 kilograms slows to a stop from an initial speed of 10 meters per second? Specifically, how much kinetic energy has it lost? To do this, we have to figure out how much energy it has to begin with. Basically, the change in energy is going to be whatever is the final energy of kinetic minus whatever was the initial energy of kinetic. And finally, it is stopped. So that means that finally it has 0 joules. So we just need to find what the initial kinetic energy is. So the initial kinetic energy is going to be 1/2 times the mass of the car times the initial speed squared. So that's 1/2 times 650 kilograms times 10 meters per second squared. Plug all these guys into your calculator or just use your brain to remember that we just found this. It's 32,500. But in case you don't believe me, let's plug these numbers in. 650 times 10 times 10. So our initial speed, our initial kinetic energy was 32,500. So now that also means that our change in energy is 0 minus this. So our energy lost is going to also be 32,500 joules. Reason why I included this example especially on the tail of that last example, is that on the last example, we found how much energy was used up in slowing from 20 meters per second to 10 meters per second. Recall that that had been 97,500 joules. That was from 20 meters per second down to 10 meters per second. This one that we just found, 32,500, was from 10 meters per second to 0 meters per second. Notice that even though the change in speed is equal, the change in energy is not. This is in fact 3 times more energy than this, because at 20 meters per second, the car had 4 times as much kinetic energy as at 10 meters per second. That's the effect of this velocity squared term right here. Now that we've worked through a few kinetic energy problems, I wanted to work a few potential energy problems. The first of these is this problem about a 7 kilogram rock 12 meters above the ground, and we want to know what is the potential energy. So in order to actually get the potential energy, we have to do something where we've defined the position where the height is 0. So I'm just going to go ahead and draw myself this diagram. And here's the ground, here's the rock. The rock is positioned 12 meters above the ground. We'll make this be height equals 0, and therefore the potential energy due to gravity is also 0 at this point. And this rock is a 7.0 kilogram rock. Recall that the potential energy due to gravity near the Earth's surface is mass times gravitational acceleration times height. So this potential energy is going to be equal to 7.0 kilograms times 9.8 meters per second squared times the height is 12 meters. And the initial problem is actually 12.0 meters, so I'm going to keep that significant figure there, even though I didn't label it on my diagram. So now we can go to our calculators to get the answer. Should be a little under 840 joules. Like maybe 20 joules less than that or so. It's estimated using 10 here. Anyway, using the calculator, I get 7 times 9.8 butterfingers times 12. So that's 823.2. And since we only can keep 2 significant figures, that means that I can write 820 joules here. Okay, another variation of this potential energy problem is that you have a stone of mass 15 kilograms. So in other words, you know what the mass is, and you know what the potential energy is, 121 joules. Question is, how high above the ground is it? Okay, again, we have to assume that there is a defined point at which the potential energy is 0, and I'm going to make that the ground. And we do not know what the height of the rock is, so I'll put a question mark next to that. Here's the rock. Mass was given as 15 kilograms, and the energy was given as 121 joules. So to solve for the height, we use that the potential energy due to gravity is mgh. Therefore, the height must be this potential energy due to gravity divided by m times g. All I've done is rearrange this equation. I basically shifted the equation around so that I say mgh is equal to epg, and then I solve for h by dividing both sides by mg. So the height is given by 121 joules divided by 15 kilograms times 9.8 meters per second squared. Okay, need my calculator. So we take 121 joules, we divide by 15 kilograms times 9.8. Gotta close the parentheses and get 0.823 meters. So the height we just solved for was 0.823 meters. So gravitational potential energy is not the only kind of potential energy. You can also get potential energy from things like electromagnetic forces, or from a rubber band, or, as this next example illustrates, from a spring. So let's figure out what the potential energy of the spring is, given that it has a spring constant of 200 newtons per meter. That's basically like a stiffness factor for the spring, and that it's been compressed by 0.250 meters from equilibrium. We want to know what is the potential. Okay, so let me just draw a couple of springs. So here is a spring that's at equilibrium. Here is a spring that's been compressed somewhat. And this distance that it's been compressed by we'll label as delta x. The spring constant is going to be labeled as k. And the potential energy of a spring is 1/2 times that spring constant times the amount that it's been compressed or stretched by squared. So that means that in this particular spring's case, we have 1/2 times 200 newtons per meter as the spring constant, times the amount that it's been compressed by, 0.250 meters squared. So now we need a calculator. So 1/2 times 200 times 0.250 squared gives us 6.25. So the potential energy of this particular spring is 6.25 joules. I want to look at a couple of conservation of energy video examples now. First conservation of energy example. We're given a rock with some mass. It falls from the top of some cliff that's 55.5 meters high. What we want to know is what the speed of the rock is just before impacting the ground below. We can make a couple assumptions. The big assumption is that the rock has fallen with an initial speed of 0. The other big assumption is that there's no air resistance or anything like that. The rock is in free fall the entire time. Let's draw a nice example here, or a nice diagram to solve this example. So here is our cliff, and this nice cliff is, I just said, 50.5 meters from top to bottom. The rock which is falling off of it has a mass of 8.2 kilograms. It's in free fall, so we use an acceleration of g as 9.80 meters per second squared. Rock is falling all the way down to here. The initial speed up here is 0 meters per second. And what we want to know is, what is the final speed down here? This would be equivalent to having a height of 0. So our conservation of energy says the following. There's no energy created or destroyed, no energy leaves or enters to the system, so therefore the change in kinetic energy plus the change in potential energy must be equal to 0. And so that means that the change in kinetic energy must be equal to the opposite of whatever is the change in the potential energy. Change in potential energy in this case is entirely in gravitational potential, and recall that that is given by mg delta h. So use the mass and use the gravitational acceleration and use the change in height, which is minus 50.5 meters. Let's go get our calculator out. So 8.2 kilograms times 9.8 meters per second times 50.5 would be 4,058.18. So delta E potential is negative 4,058.18 meters. Okay, the change in kinetic energy is going to be given by 1/2 times the mass times the final speed minus 1/2 times the mass times the initial speed. This whole term is 0 because the initial speed was 0. So therefore the kinetic energy change has to be whatever is 1/2 mv final squared. So that means that the final speed squared is equal to the negative change in the potential energy times 2 divided by the mass. This is because if 1/2 mv final squared is equal to E potential, then mv final squared must be twice the potential. V final squared must be twice the potential over m. So at that point we have that the final speed must be the square root of all that stuff. So 2 delta E potential, so twice the change in potential energy divided by the mass. We're taking the square root of everything. This means that the final potential this means that the final speed must be 2 times 4058.18 joules divided by 8.20 kilograms. Calculator time. We have this times 2, and that has to be divided by 8.2. Now we need to take a square root. So that's 31.46, and we need to round it off to 3 significant figures. So the final speed is about 31.5 meters per second. That's the speed that it would be hitting the ground with. Let's look at a different conservation of energy problem now. This one has a spring in it. So we have a spring that is launching a pinball. And the reason why I put this example in is because that previous example we actually could have solved without ever using the mass. I'll leave that as an exercise to the viewer to do, or to show that that can be done, but you actually didn't need the mass in the previous example. In this example, you do need the mass. So let's look at this example with a spring that's being used to launch a pinball. Alright, so spring is kind of tightly coiled. It's going to launch this pinball. And in so doing, the spring has to basically uncoil, and the spring is going to uncoil by 0.50 meters. By uncoil, I basically mean stretch. And the pinball itself has a mass of 0.5 kilograms, and the spring had a spring constant of 100 newtons per meter. Okay, so now what we need to do is figure out what speed this pinball gets launched at. So again, we're going to use conservation of energy. And for that conservation of energy, what we have is basically that the change in potential energy plus the change in kinetic energy is equal to 0. Again, there's no work being done by friction, no outside forces to the system, etc. So again, what this means is that the change in kinetic energy must be equaled by the change in potential energy, but such that if this gains, then this loses, and vice versa, hence the negative sign. And this change in kinetic energy we could write as 1/2 mv final squared, that's the final kinetic energy, minus the initial kinetic energy, must be equal to the negative of the final potential energy minus the initial of the potential energy. Which all written out looks like this. Now, we're given that the ball is initially at rest, so this term goes away. the position at which the ball leaves from the spring is also 0. So what that means is that 1/2 the mass of the ball times the final speed of the ball squared is equal to a negative of negative 1/2 times the spring constant times the initial displacement from equilibrium of the ball. So there's a half here and there's a half here. There's a negative here and a negative here, so those things cancel. The mass of the ball times the final speed of the ball squared is going to be the spring constant times the displacement from the equilibrium squared. That means that the final speed of the ball squared is this ratio, which is spring constant times displacement squared divided by mass. So if I want to get rid of the squared parts, I take a square root of both sides. Okay, so that means that the final speed is whatever is the square root of 100 newtons per meter times 0.150 meters squared divided by 0.5 kilograms. Stick all that into the calculator. What you get is 100 times 0.15 squared divided by 0.5, and then we need to take a square root. That's 2.12 meters per second. So the final speed is going to be 2.12 meters per second. That gives us the final speed of the ball once it's launched by the pinball machine. I'd like to finish this set of worked examples by looking at a few examples that have to do with average and instantaneous power. And actually, of these, the first example is how many joules are in a kilowatt hour. This one is not so much to illustrate power per se. I mean, basically 1 kilowatt hour is the equivalent of saying you deliver a power on average of a kilowatt for a time of an hour, but it's actually a unit of energy, and so it doesn't necessarily involve delivering 1 kilowatt of power over the course of 1 hour. It could be 2 kilowatts of power delivered over the course of 30 minutes continuously. Could be 36,000 kilowatts delivered in a second, etc. So what we want to know is how many joules this is equal to. So this is basically a unit analysis problem. 1 watt is the same thing as 1 joule per second. So 1 kilowatt hour is the same as taking 1,000 watts and multiplying by 1 hour. And so we want to know how many joules that is. Well, that's the same thing as saying 1,000 joules per second times 1 hour, which is the same thing as multiplying by 60 minutes per hour. And there's 60 seconds per 1 minute. So that means that what we have is 1,000 times 60 times 60, 3,600,000. So 1 kilowatt hour is the same thing as 3,600,000 joules. So when the power company charges you for a number of kilowatt hours, they're really charging you in terms of how many times 3,600,000 joules have you used. Another example which uses power is this laser pulse example. So you have a laser pulse whose duration is 8 nanoseconds. It has an energy of 1.2 joules, and it has 10 pulses per second. By the way, this is very nearly the parameters of a typical neodymium YAG pump laser of the sort that I used to use when I was doing high energy laser physics. Actually, they typically would have anywhere between half a nanosecond and maybe 10 nanoseconds, but 8 was not a bad estimate. They were about 10 pulses per second, and the energy was anywhere between 1 and say 1.5 joules per pulse. So trivia aside, how do you figure out the peak, which is instantaneous power, and the average power? Okay, the average power is defined as the amount of work done per unit time, which is the same thing as the amount of energy available per unit time, according to the work energy theorem. So what we had here was a 1.2 joule per pulse laser times 10 pulses per second. So that 10 pulses per second, that per second is where the delta T comes from. The delta E is how many joules per pulse and how many pulses are delivered in that second. So this means that the average power is 1.2 times 10, or 12 watts. Okay, what about the instantaneous power? Well, the peak power or the instantaneous power basically needs to be a power delivered in some duration of time that's very, very short. So 8 nanoseconds actually is a very short amount of time. So strictly speaking, if we treated these as being a pulse that was same amount of energy per time so long as there's a pulse, then what we need to do is take the energy of a pulse and the time of a pulse. So that would be 1.2 joules per pulse divided by 8 nanoseconds per pulse. Or I guess this was 8.00 nanoseconds. So the per pulse part goes away. This is the same as 1.2 joules divided by 8.00 times 10 to the minus 9 seconds, because a nanosecond is 1 times 10 to the minus 9 seconds. Okay, so that means that the peak power of such a pulse is going to be given by 1.2 joules divided by 8 nanoseconds. That was just divided by the 8 part, so now I've got to put in the nanoseconds part. The way that I do that is I'm going to use this 10 to the x function, but I need to have the power first, and then I put in the 10 to the x. And so I come up with this number, which is actually about 1.50 times 10 to the 8 watts. So 0.15 gigawatts. Okay, that's assuming that the pulse is what would be called a square pulse, meaning same power per unit time for the entire duration of the pulse. I should add as a piece of interesting trivia that usually the pulse shape is not necessarily square. They usually sort of have a rising edge, they have a peak, and then a tapering trailing edge. Oftentimes this pulse shape looks like a bell curve. It's basically called a Gaussian pulse, in which case you have to basically do something a little more tricky to get this peak power. Sometimes you can multiply by a simple factor like 2. Sometimes the pulse is not so easy shaped, and then you have to use calculus to find the answer. So I would suppose I would save that for a higher order math physics class, like the introductory physics class with calculus. That would be the physics class that our freshman physics majors take, and maybe sophomore or junior majors in chemistry, that kind of thing. But it is definitely too advanced for this physical science class to attempt, because we are limited to algebra methods at most. Okay, last example that deals with power is this question: how much energy is used by a 60-watt light bulb in 1 minute? So a 60-watt light bulb basically means that it's using 60 watts of power continuously for the amount of time that it's running. So power, of course, is basically going to be the amount of work done per unit time, or in this case is basically the energy used by the bulb per unit time. So if we want to know what the energy used is, then we can take what that power was and multiply by the amount of time that it runs for. So the energy used is going to be 60 watts times 1 minute times, recall that a watt is a joule per second, so instead of putting this in minutes, we're really going to want it in seconds. So we're going times 60 seconds per 1 minute. And that means that the energy use is going to be 60 times 60 should be 3600. So the energy used will be 3600 joules. So that's how much energy you're using each minute with your 60-watt light bulb. Notice that this is basically 1/1000th of the energy I solved for earlier when finding the amount of joules go into a kilowatt hour. So basically, if you use your 60-watt light bulb for 100 minutes, you've burned through 1 kilowatt hour of energy. So that's all the examples that I wanted to work through today. Thanks for watching this video. I hope you found it helpful.